Hey, Dr. Zhang. So we're back for our fourth heat transfer project. It's going to be on convection, and we are back with the trusty temperature gun, which works okay, not great, and we're back with the burner. So what we're going to do is I'm going to crank this baby up to maximum temperature, and we're going to figure out the convection coefficient and see if this wind is strong enough to keep the burner from heating up all the way to its maximum temperature. It's about 52 degrees outside, and the wind speed has gusted up to 15 miles per hour, and we're getting some good gusts right now. So, I'm going to take a temperature. And the temperature is 535 degrees Fahrenheit for the surface. So we're gonna get this plate measured up so we can get the length and the width, and the wind is coming in like that. So this will be the length and this will be the width. All right. So we have the good old math for this convection problem. So let's get looking at it. We have our wind speed and our temperatures that we measured, and then the average temperature of those two, which we use for the values of the air. We have the amount of heat that comes out of the burner, and we have the dimensions of the area of the burner. So our big equation is Q equals HA times delta T. That's the big one. So we need to find H. So we're going to find H bar, and to find H bar, we need to find Q bar. And Q bar is the heat flux. So the heat flux is Q divided by area, which is 7,751.9 watts per meter squared. And then our delta T is just T wall minus T infinite. Alright, so now we need to find H bar. So for H bar, we need Nusselt's number. For Nusselt's number, we need Reynolds number. And we can find Reynolds number. So we have to go to the air charts in the book and find viscosity, because we have U infinite and L. So there's the viscosity at 417.75 Kelvin. And so that's Reynolds number. Then we can find Nusselt's number, and all we need is Reynolds number from the charts. That's right there. There's Nusselt's number. And our H is going to be Nusselt's number times K divided by L. So our H is 19.85 watts per meter squared times Celsius. Alright, so once we have our H, we can plug it all in here, and here's our ending result. So the amount of Q that the burner can put out is greater than the amount of Q that came out. And the burner has a sensor that cuts off when it gets to a certain temperature, and it never cut off. So it leads me to believe that there's an efficiency that I do not know about that the burner has. So it takes in 1,000 watts, but doesn't necessarily put out 1,000 watts. Or it reached its limit and the sensor wouldn't let it go over. So overall, here's the experiment. I had fun doing it. I hope you have fun watching it.